Chapter 30: Quantum Physics. Here is the overview of Chapter 30. We will first talk about black body radiation and how that led to the hypothesis for quantized energy. We will then talk about photons and the photoelectric effect, which were further evidence of quantized energy. Then we will talk about the mass and momentum of a photon, move on to the photon scattering and the quantum effect. Then we will discuss de Broglie's hypothesis and wave-particle duality, move on to the Heisenberg uncertainty principle, and we will finish on quantum tunneling, which is an application of the uncertainty principle. A black body is a material that will absorb all the light that is incident upon it. Here we have an example of a box. We see that light enters the box, but it doesn't escape as it enters through a very small cavity and continues to be reflected within that cavity. There is actually a temperature associated with the radiation in the box, which we refer to as T, and we will discuss more in the next slide. A black body is also an ideal radiator. By that, we mean that if we heat a black body to a particular temperature, we will see the radiation of a variety of electromagnetic waves. On the top, we have two black body spectra. One corresponds to a black body, which is the red spectra of 3000 Kelvin, and the yellow spectra corresponds to a temperature of 6000 Kelvin. On the x-axis, we have the frequency, and the y-axis is the relative intensity. We can see as we heat a black body from a lower temperature to a higher temperature, the relative intensities of the higher frequencies will be greater for the body of the higher temperature. That's shown when you compare the black bodies of 3000 and 6000 Kelvin on the top, and then when we go to the bottom, we compare a black body of 6000 and 12,000 Kelvin. We can see that the relative intensity of, say, a frequency of 15 by 10 to the 14 hertz is much greater for the black body of 12,000 Kelvin compared to 6,000 Kelvin. Now, this observation illustrated a remarkable experimental finding. That is that the distribution of energy in a black body radiation is independent of the material from which it is constructed, and it only depends on T, the temperature, as a result. Now, the peak frequency, which is the frequency with the highest intensity at a given temperature, is given from Wien's displacement law, which states that that peak frequency is equal to 5.88 by 10 to the 10 seconds to the power of -1 times Kelvin to the power of -1 times the temperature. So the peak frequency is linearly proportional to the temperature. Now, as stated, since the peak frequency increases linearly with the temperature, that means that essentially the temperature of a black body can be determined by its colour. The colour of the black body is essentially the frequency that we see. One example would be the sun. The peak temperature for a body of 6,000 Kelvin, which corresponds to the surface temperature of the sun, is a frequency that has the wavelength of yellow light, and that's why the sun appears to be yellow. Now, this caused a problem in the classical physics calculations, and they were completely unable to reproduce this temperature dependence, and it led to something called the ultraviolet catastrophe. So here we have an example of this disparity. For the plot, on the y-axis we have the relative intensity of electromagnetic radiation, and on the x-axis we have the frequency of the electromagnetic radiation for a black body. What we observed in experiment is the curve with the green colour, and what was predicted with classical physics is the curve with the blue colour. We can see at lower frequencies there is a difference between the two, indicating that these classical predictions are not correct. What we find in particular is the classical predictions predict something that increases very rapidly with frequency. However, the data, which is the green curve, doesn't increase as rapidly and actually falls off at higher frequencies. This curve is also consistent with Planck's prediction, which we will discuss on the next slide. Regarding the Planck prediction on the previous slide, essentially Planck discovered that he could reproduce the experimental curve by assuming that energy came in quantized energy packets which depended on the frequency. This means that the possible energies a particular frequency can occupy are actually limited, and they are limited by the equation En, which is the energy that we're interested in, is equal to n, which is an integer, times h, which is a constant, times f, which is the frequency that we're interested in. The constant h is known as Planck's constant, and that is equal to 6.63 by 10 to the minus 34 joule seconds. Essentially, classical physics does not have this restriction on energy, and because of that, that's why there are different predictions for quantum physics, which is essentially the approach of Planck, and classical physics, which, as I said before, has none of these extra restrictions that Planck imposed. Now, there are a few points to make about Planck's approach. The first is that Planck's constant is a very tiny number. It's a number that goes to 10 to the power minus 34, and it's actually the smallest number you will encounter in this course. That essentially means that these quantization or the quantization of energy is not something that's easily observed in most macroscopic situations where larger numbers are more applicable to describe the various things that we see. It also puzzled many people at the time because they did not know where this quantization or this restriction came from. Why did nature suggest that we should do this, and why, when we do this, do we describe the radiation data as well as we do? Now, Einstein suggested that this quantization of light was real, and that light came in small packets, which we now know as photons. These photons have a particular energy, and that energy is equal to E, which is equal to Planck's constant h times the frequency of the photon f. This means that the n that we talked about in the Planck approach essentially corresponds to the number of photons that we have. This essentially means that a more intense beam of light will contain more photons, but the energy of each photon will not change. This is fixed, and it's fixed by the value hf that we showed before. An example of a low intensity beam might have 2 photons, and a high intensity beam might have 5 photons, but the photons in each case will all have the same energy. Something that really did demonstrate that light consists of photons is the photoelectric effect. This occurs when a beam of light strikes a metal. After that, electrons from the metal are ejected and they move away. Each metal will have a minimum amount of energy that is required to reject a single electron, and this is known as the work function W0. If the electron is given an energy E by a photon, then its maximum kinetic energy will be the energy of the photon, E, minus W, the work function. This simply comes from energy conservation. Here we have a basic diagram that demonstrates the photoelectric effect. What we have is incoming light at the top, and this is shone onto what we call a emitter, which is a metal plate on the right. Photons can then be released and they move towards the collector, and the movement is essentially caused by the battery, which is giving an EMF, and the positive side of the battery will essentially mean that the collector will be positively charged, and this positively charged collector will attract the electrons emitted from the photons. In this process, we will record a current, and that current will be recorded by the ammeter that is shown. Without the photoelectric effect, there is no current because there is no way for electrons to travel from the emitter to the collector. Now, the classical predictions for the photoelectric effect imply that any beam of light of any color can eject electrons if that beam is intense enough. A second prediction is the maximum kinetic energy of an ejected electron should increase as the intensity increases. Now, if you look to see what we observed that light must have a certain minimum frequency in order to start ejecting electrons, and when the light is more intense, we have more electrons that are emitted, but these electrons all have the same energy. So when we compare the classical prediction to what we observe, we see a big discrepancy, essentially. So from the quantum physics point of view, here are our explanations. The first is that each photon's energy is determined by the frequency. If this energy is less than the work function, which is the energy needed to release an electron, we simply cannot release or eject an electron from the metal, no matter how intense the beam. The cutoff frequency F0, which is the minimum frequency we can use to eject an electron, is W0, which is the work function, divided by Planck's constant. Here we see the maximum kinetic energy of an electron as a function of the frequency of the photons or electromagnetic radiation that's been shone onto the metal. Different metals have different work functions. It turns out that sodium has a smaller work function than gold, which means you need less energy to eject electrons. As we increase the frequency of the photons, we find the maximum kinetic energy increases on a linear basis, which is expected from the quantum physics point of view. Now, an explanation for the second observation that we have is a more intense beam means more photons, and if there's more photons, we'll have more ejected electrons, all of which, as we said, have the same energy because the photons will have the same energy for a given frequency. Now, despite the fact photons have no mass, they actually have momentum. This is determined in chapter 29, which is not something that we study in this course, but it comes out of the equations of relativity, where you can actually show that something can have a momentum but no mass. The momentum of the photon P is equal to Planck's constant h times the frequency f divided by its speed c, or it's equal to h over lambda, where lambda is the photon's wavelength. The Compton effect essentially occurs due to the fact that a photon indeed has momentum, and it can give some of its momentum to an electron after a collision. What happens, as shown here, is an incident photon on the left moves towards the electron. It hits the electron gets some of the momentum of the photon and travels downward, and the scattered photon, which is traveling to the top right, travels with less momentum, and the difference in momentum is equal to the extra momentum is given to the electron. Because the photon's momentum has reduced, it turns out that its wavelength has to be bigger. Now, you can also look at this from the point of view of energy conservation, and in order for energy to be conserved, the energy of the scattered photon plus the energy of the scattered electron must equal the energy of the incoming photon. This also implies that the wavelength of the outgoing photon has to be longer than the incoming one, because the wavelength is also related to the energy. The larger the wavelength, the smaller the energy of the photon. This change in the wavelength is described by the Compton shift formula, and the change is represented by delta lambda, which is equal to lambda dash, the wavelength of the scattered photon, minus lambda, which is the wavelength of the incident photon, and that's equal to h, the Planck's constant, divided by me, the mass of the electron, times the speed of light, c, times open bracket 1 minus cos theta close bracket, where theta is the scattering angle we saw in the previous slide. In 1923, someone called de Broglie proposed that as waves exhibit particle-like behavior, particles should exhibit wave-like behavior as well. This is what we mean by the hypothesis of wave-particle duality. Now, by waves exhibiting particle behavior, the best example of that is the Compton effect, where a photon, which is part of a wave, can hit an electron and scatter off, just as another electron, which is a particle, could also hit the same electron and scatter off as well. He proposed that the same relationship between the wavelength and the momentum should apply to particles as well as photons. So a particle's wavelength, lambda, is equal to h, the Planck's constant, divided by p, the particle's momentum. Exactly the same equation applies to photons as well. A photon's wavelength, lambda, is equal to h divided by p, where p is the photon's momentum. Now, the correctness of this assumption has been verified many times over. One example of particles behaving like waves is they are actually able to show diffraction patterns. In this example, we have diffraction from a crystal, and as we discussed before in the previous chapter, when X-rays are shone on this crystal, we see a diffraction pattern behind it from the reflected beam. Now here's another way of showing the pattern, where we have X-rays, or indeed particles that pass through the crystal structure. We see our interference pattern behind the crystal on the photographic film. This pattern will be exactly the same, irrespective if we use X-rays or particles, as long as the X-rays or the particles have exactly the same wavelength. We can also perform Young's two-slit interference experiment with either particles or waves. Again, if the particles or the waves have exactly the same wavelength, we expect exactly the same diffraction pattern. Now, with a wave, we will see bands of light and dark. With particles, we will see areas where there are many particles and not so many particles. And it turns out, for the Young's split experiment, when we use light, the bright spots correspond to where there are many photons, and the dark spots correspond to where there are few photons. What's really amazing about this experiment with a particle beam is that if we reduce the beam so only one electron at a time passes through the experiment, the electron will still exhibit a two-slit pattern and not a one-slit pattern that we see in the diffraction experiment. This is pretty amazing and quite confusing, because one would think if there's only one electron at a time, it can only pass through one of the slits, therefore it will exhibit a one-slit pattern, but that is not the case. A two-slit pattern is exhibited, and it appears the electron itself is passing through both of the slits. Now, as the diffraction pattern builds, we can't predict where a single electron or particle will land, but we can predict the final appearance of the pattern when we have many particles or electrons. Here we have an example of the Young's two-slit experiment with electrons. What we do is we have an electron beam, and then we record where the electrons land after various time intervals. On the left, this is a short time after the beam is switched on. Then the middle, this is a longer time. And then on the right, this is an even longer time, and we can see the emergence of a diffraction pattern where there are areas with many electrons and areas with few electrons. This effect essentially leads us to something called the Heisenberg uncertainty principle. The implication is that if we have a beam of electrons and we try and make the electron pass through a slit with a particular width W, then this will introduce an uncertainty to the momentum, which will be in the y direction in this example as the width is in the y direction. And this simply comes due to the fact that the electron will diffract. This is one of the most important principles in quantum mechanics and essentially comes from the wave properties of the matter. So what we're saying is when we try to determine the position of an electron by forcing it through a slit, we introduce an uncertainty to the momentum, because when the electron passes through, it can diffract either upwards or downwards, and we don't know where it's going to go. The uncertainty itself is shown by delta Py, which is the possible momentum the electron can gain in the y direction after it diffracts. So, as mentioned on the previous slide, electrons diffract through the slit. They acquire a y component of momentum that they had not had before. This is essentially the uncertainty principle. Another way to put this is to say that if we know the position of a particle with greater precision, its momentum is more certain. If we know the momentum of a particle with greater precision, its position is more certain. Mathematically, this translates to delta Py, which is the width of the diffraction pattern in terms of the momentum, times delta y, which is the width of the slit, has to be greater or equal to h, Planck's constant, divided by 2 pi. The diagram shows what we said before. If you look at the top pattern, what we have is we have a small delta y, which means that we know the position with much more precision. However, this leads to a wider diffraction pattern and a wider uncertainty in the momentum. We have a larger delta Py as a result. If we try and widen the slit to get a greater delta y, which is shown on the bottom, this means the position is more uncertain, but we will have a smaller diffraction pattern, and as a result, a smaller uncertainty in the momentum, delta Py. We can also restate the uncertainty principle in terms of energy and time rather than position and momentum, and it turns out that this inherent uncertainty in energy times and uncertainty in time has to be greater or equal to h Planck's constant divided by 2 pi. Generally, the effects of the uncertainty principle are not noticeable in everyday macroscopic situations, and this simply due to the fact that Planck's constant is very small, so these uncertainties themselves are very, very small. Quantum tunneling is essentially an example of the wave-particle duality that we described before. So a property of waves is sometimes they can tunnel through gaps that they would otherwise not be able to traverse. Here we have an example where a wave is within a medium, and the wave will often get reflected from the boundary of the medium. If we put another material which has the same medium close to the wave, sometimes the wave will jump from the left medium to the right medium. As we widen the gap between the two mediums, this effect, or the probability that the wave will jump from the one medium to the other, will decrease exponentially with the size of the width. Given their wave-like properties, it should come as no surprise that particle can tunnel as well. A practical application is the scanning tunneling microscope, and this is used to create images of single atoms by tunneling of electrons. What we have on the bottom is the tip of the microscope, and this tip is scanned along an atomic surface. When the tip is next to the high points of the surface, we have a lot of tunneling and essentially a lot of current. When it is over a low point, we have less tunneling and less current. So we can essentially measure the current in the tip, and this tells us the surface profile of the atomic surface that we are interested in.